All right, so previously we said that if you have a volatile component of a liquid mixture, you can determine its activity by simply measuring its partial pressure in the vapor that's in equilibrium with your liquid mixture and divide that by the vapor pressure of that component if it was pure. Okay, so activity of liquid A, for example, as part of a mixture would be whatever its partial pressure is above that mixture divided by its vapor pressure if it were pure. Okay, and we also said that in the limit of uh, mole fraction of A approaching 1, it's very then so when you have a mixture that is almost pure A, okay, then it tends to obey Raoult's law, so that the partial pressure of A over its pure vapor pressure is equal to the mole fraction. In other words, the activity of A is just going to be equal to the mole fraction of A. Okay, so we can also rewrite Raoult's law. We can rearrange this equation. We can say that the partial pressure of A is equal to its pure vapor pressure times the mole fraction of A. Now, we said that if you have an ideal mixture, then if you have a mixture where this is obeyed, okay, then you have what's called an ideal mixture. Now, what if A is a solute instead in a very dilute solution? So in other words, let's not take a look at a case where X of A approaches 0. Okay, in these cases, we say that typically in these cases, your partial pressure of A you'll find it to be directly proportional to the mole fraction of A, and this relationship is known as Henry's law. In other words, the dilute solution, solutes in dilute solution tend to follow what's called Henry's law. Okay, so P sub A over X sub A, partial pressure of A, so if you have a mixture of A, dilute solution of A plus, there's a lot of other stuff there, in equilibrium with gases A, okay? The solid, in other words, the mole fraction of A in the liquid is directly proportional to its vapor pressure. Another way of saying it is the vapor pressure, okay, of A, or the concentration of A, or the solubility of A in the mixture is directly proportional to the vapor pressure of A above the mixture. Okay, now it turns out this Henry's law constant, which we're writing here as K sub H prime, is not necessarily equal to P star A. And the explanation for that has to do with the fact that solute molecules, okay, may have greater or lesser tendency to escape from the liquid if it is surrounded by solvent molecules. Let's try to relate that to Raoult's law. Remember we said that if you were to plot partial pressure of A versus mole fraction of A, okay, if it were to obey Raoult's law, then, okay, here you have partial pressure of A pure, and it starts up at 0 here. Okay, you say if it obeys Raoult's law, then P sub A equals P sub A star times XA. Okay, it turns out that, okay, at very dilute solutions, we're dealing here with dilute solutions right here, okay? It turns out that if you were to plot P sub A versus mole fraction of A, you're going to get either a positive deviation, okay? The slope is either more positive or less positive. You have a negative deviation, okay? So why would that be? The molecular level explanation for that has to do with the fact that here in very dilute solution, you have a solute molecule of A. It's going to be surrounded by mostly its main environment is mostly solvent molecules. Let's say B would be your solvent molecules. Whereas over here, when you nearly have pure A, it will be surrounded by others of the same kind, primarily. Okay, so this molecule right here in a dilute solution will have a different tendency to escape from the liquid as opposed to this solute molecule right here that's mostly surrounded, this solvent molecule over here. Okay, the same molecule surrounded by others of the same kind. And so it depends on the attractive forces between the A and B molecules. So solute-solvent interaction plays a role in this deviation from Raoult's law. Okay, so if you have strong solute-solvent interactions, you would expect a negative deviation. You would say your solute will have lesser tendency to escape. Okay, if the solute molecule doesn't like the solvent molecules, then it will have a greater tendency to escape. It will have a higher vapor pressure. Okay, so let's say you have a positive deviation from Raoult's law. And so let's say this is this graph right here. Let me get rid of this. So let's say this graph right here is our Henry's law. So what would happen if we were to extend that line all the way to pure A, mole fraction of A equal to 1? Okay, if we extend that line all the way there, then when x of A is equal to 1, then remember P sub A over x of A is equal to KH prime, right? So when x of A is equal to 1, then the value here of the partial pressure of A would be equal to KH prime. In other words, one way you would interpret KH prime is that would have been the partial pressure of pure A if Henry's law were to hold all the way to pure A. But of course, we know that that's not going to happen. But it's convenient to define that as our standard state. Okay, so in other words, what we're going to do is we're going to use that as a basis for defining a standard state. And so we're going to say that all of the solutions that obey Henry's law, so if your data would correspond to a point on this line right here, let me get rid of this other equation, Raoult's law. Okay, if your data, the vapor pressure data for your solutions would fit this line for Henry's law. In other words, if your solution obeys Henry's law, we say it's an ideal dilute solution. Realistically, we expect that to be obeyed only down here at very dilute solutions. Okay, so this would be right here, for example, you would call that, if let's say you happen to have a mixture that has this mole fraction of A, and it falls on this line right here, okay, and you measure the vapor pressure of A, it's that. So then we say that would be an ideal solution in the Henry's law convention. Okay, so as far as Henry's law is concerned, that would be considered an ideal solution, but as far as Raoult's law, that's not an ideal solution. Okay, so if we can define our fictitious pure liquid with a vapor pressure equal to KH prime as a standard state for solutes. Okay, so the activity of a solute, then a volatile solute in a real solution, can be written as whatever its partial pressure is above that solution divided by KH prime, where KH prime is what its vapor pressure would have been if it were pure and Henry's law were applicable all the way up to mole fraction equal to 1. Okay, so let's illustrate that by this example. Vapor pressure of acetic acid, pure acetic acid liquid will have a vapor pressure of 15.73 torr at 298 at room temperature, 298 Kelvin. But in water, if you were to dissolve acetic acid in water, the Henry's law constant for acetic acid will only be 4.2 torr. Okay, and so let's see what that would look like if we were to sketch the vapor pressure of acetic acid versus mole fraction of acetic acid. Mole fraction of acetic acid 0 to 1. When it's pure acetic acid, your vapor pressure is equal to 15.73 torr. Okay, so if Raoult's law were to be valid, it would look like that. Okay, so let's make that your 15.73 torr. Now, if you have dilute solutions of acetic acid in water and you measure the partial pressure of acetic acid in the vapor, you'll find that it's going to have a negative deviation from Raoult's law. In other words, this is what you'll find. Okay? Right here. And if you were to stretch this out all the way, this straight line right here, all the way to mole fraction of 1, you'll get the value of Kh prime, which is 4.2 torr. Okay? Now, that doesn't mean that solutions of acetic acid in water will have vapor pressures given by this line. Okay? What we know about Henry's law is it tends to be valid at very low concentrations. So a real solution might have your vapor pressure right here or right here, okay, or right here. So it's not going to be on that line, exactly on that line. So if you have a solution that it happens to be on this line, then we say it's an ideal dilute solution, okay, as far as Henry's law is concerned. So what's the interpretation of the negative deviation from from Raoult's law? Then what we're saying is that your acetic acid over here is surrounded by water molecules. Okay, so it has less tendency to escape. Okay, its vapor pressure is lower than what it would be if Raoult's law was obeyed. So that suggests a strong attractive forces, strong attractions between the acetic acid and the water molecules. And you can explain that using the structure of acetic acid. There. So you can have hydrogen bonding interaction between this hydrogen and a lone pair on the oxygen atom of a neighboring water molecule. Okay, this oxygen lone pair here can interact with a hydrogen atom on a neighboring water molecule. This oxygen right here could interact with the hydrogen of a neighboring water molecule. And so can this one. And this one as well. Okay. So there's at least 5 different places in the acetic acid molecule where you can have hydrogen bonding interaction with water molecules. Now, the basic idea behind Henry's law is that the vapor pressure of a volatile solute is directly proportional to its concentration. And there are many ways of mathematically expressing this idea. And what we wrote so far is one where we use mole fraction as a unit, as our concentration. So we have expressing our concentration. That's not the only way of doing it. So if you remember when we did this, we said that PA over XA is equal to KH prime, right? So the ratio of 2 quantities is a constant. It means that they are directly proportional. I could have written this as XA over PA equals some constant, okay? So this would be another mathematical way of writing the Henry's law. And so your constant here would be equal to 1 over what we would call KH prime up there, okay? So what you might actually, if you were to look up Henry's law constants, you might actually find the value of 1 of K over KH prime instead of KH prime. So you have to be careful when you're looking up Henry's law constants. The unit for KH prime would be a unit of pressure, like torr or atmosphere. But if you found a Henry's law constant from the literature and you found it to be given in reciprocal torr or reciprocal atmosphere, then this must be the expression that was assumed. Okay? And mole fraction is not the only way to express concentration. You can use molality. So you can say that the partial pressure of A is directly proportional to its molality. And we're going to call the constant for this the proportionality constant K sub H. Okay, this is the more popularly used constant. And so what would be the unit for this? This would be a pressure unit, so that would be torr over molality unit would be mole solute per kilogram of solvent. So if you were to look up Henry's law of constants and you find that it's a pressure unit divided by a molality unit, then this must be the expression that's being assumed, that's being used, okay, for that particular constant. So anyway, let's take a closer look at this expression right here where your partial pressure is expressed in terms of molality. Okay, what the Henry's law, let's relate the k sub h here to k sub h prime. All right. Now, the thing to realize is in very dilute solution, the mole fraction of your solute will just be approximately equal. So a very good approximation is going to be equal to its number of moles of the solute divided by the number of moles of the solvent. Why is that? Because the number of moles of solute will be very small compared to the number of moles of solvent. So in other words, your number of moles of solvent will just be approximately the total number of moles. Okay, so if that's the case, then you can relate that to the molality. If you remember, molality means moles of solute per kilogram of solvent. So in this particular case, moles of solute would be moles of solute per kilogram of solvent, which is the molality, times however many kilograms of solvent I have. Okay, so that's what you have right here. That's moles of solute. And moles of solvent would be however many kilograms of solvent you have divided by the molar mass of the solvent, which has to be given in kilograms per mole. So keep in mind that this must be in kilograms per mole, so your kilograms will cancel out. So if you divide this, kilogram solvent is going to cancel out. So kilogram solvent cancels out here. You'll just have molality divided by 1 over molar mass. So it's just molality times the molar mass of the solvent. And that's the expression for your mole fraction, in terms of the molality in very dilute solutions. So if that's the case, let's relate KH and KH prime now. So we say PA, partial pressure of A, is equal to KH times molality. We're going to solve for molality here. Okay, so here X of A equals molality times molar mass. So X of A is molality times molar mass of the solvent. So molality is X of A over molar mass of the solvent. So I'm going to substitute this for molality over here. And so I get K sub H times molality, which is X of A divided by molar mass of the solvent. So you can see here then that K sub H over molar mass of solvent is just KH prime. That's how it's related. So if you can look up the value of K sub H, then you can convert it to K sub H prime by just dividing it by the molar mass of the solvent in kilograms per mole. Let's illustrate that. Here you have acetic acid. Okay. If you look up the Henry's law constant for acetic acid, this is actually the number that you'll more easily find. It's 0.076 torr per molality. Mole per kilogram is molality. So how do you calculate KH prime? What's our formula? It's just KH divided by molar mass. Okay, so it's just going to be K sub H divided by the molar mass. And if you don't remember whether to multiply or divide, you can always just check using unit dimensional analysis if your formula is correct, if your units are consistent. So K sub H is 0.076 torr. Okay, let me make this per mole times kilogram, because mole per kilogram is in the denominator there. And molar mass, and don't forget, this is molar mass of the solvent, so we're dealing with water here, so molar mass is 18.02 grams per mole, right? But we have to put that in kilograms, so it's going to be 18.02 times 10 to the negative 3 kilograms. Negative 3 kilograms is a gram. Okay, 10 to the negative 3, 10 to the third kilogram would be a gram. Okay, So kilogram per mole. So mole cancels out, kilogram cancels out. That gives you your KH prime in torr. So that should give us a value of, let's see, what would that be? 0.076 divided by 0.01802, 4.24, which is what we had earlier. Okay, let me show you some websites where you can find Henry's law constants. Just do a Google search. So I just do a search for Henry's law constant in Google, and this is what you'll get. Here's one that takes you to henryslaw.org. So if you look at this website, okay, and you'll notice there's many different ways of expressing the Henry's law constant, so different units. So if you're interested in KH prime, the unit you want is a pressure unit. So what he calls here the K sub H comma inverse PX, that's the ratio of the partial pressure to the mole fraction. Okay, that will give you a unit in atmosphere. Okay, and if you're dealing with partial pressure, mole fraction over partial pressure, then your unit would be reciprocal atmosphere. So if you're gonna, this is what we called KH prime, right? And what's the one that involves K8, just molality and partial pressure? That would be pressure over concentration. It would be this one. This is what we call K sub H. Okay? Partial pressure over concentration. So this is not quite the same because this is moles per cubic meters, and he's using all SI here. Okay? And it's not per kilogram because he's using molarity. Okay, so this is not the same as, but well, this is practically the same as our KH, except that the unit here is per liter, because at very dilute aqueous solutions, okay, molality is approximately equal to molarity. So molality in very dilute aqueous solutions is approximately equal to the molarity. So you can use that as your K sub H. All right. And let's see some other websites where you might find some information on Henry's law. Henry's law constants. There's one right here. Okay. This is a PDF file. Okay. From the Max Planck Institute of Chemistry. So there's some Henry's law constants, which actually tells you also how it depends on temperature. Okay, so for oxygen, let me see if I can zoom in here. I believe these are all just values in water. So it's 1.2 times 10 to the negative 3. Okay, and the unit here is molarity per atmosphere. Okay, so that would be KH. Since there are two ways that you can express Henry's law, you can express it in terms of molality. You can say partial pressure of A is equal to K sub H times the molality, or K sub H prime times the mole fraction of A. We can define two possible standard states for solutes. And so one way we can say is our standard state, that means our activity would be equal to 1, would be one where the molality is equal to 1 and the partial pressure of A in equilibrium with the mixture is equal to K sub H. Okay. We divide K sub H by M naught. We define M naught to be a 1 molar, Okay. So the other convention is to say we're going to define our standard state as the case where you have pure A and its vapor pressure is equal to K sub H prime. You can base your definition for activities in either one of those two cases. So activity for a solute then in an ideal dilute solution would be whatever its molality is divided by M naught. Okay, and like I said, for very dilute solutions, molality in aqueous solutions, very dilute aqueous solutions, your molality will just be equal to your molarity. Now, if you use the second convention, then your activity will just be the mole fraction. Okay, and that's if you have a solution that is ideal dilute. Of course, if your solution is not ideal dilute, then you have to introduce an activity coefficient there, gamma. And regardless of which convention you use, you are going to get the same activity coefficient, because in one particular case, you're going to say the chemical potential is equal to chemical potential plus RT ln molality over M naught. So your activity is M over M naught. And then the correction term you're going to add would be, if it's not ideal, would be RT ln gamma. Well, you can also say chemical potential is mu naught prime, okay, plus RT ln XA. And then your correction term there is going to be RT ln gamma. In either case, if you are deviating from ideal behavior, you're going to get the same value for gamma. So how are you going to measure your gamma? How are you going to determine your gamma? All you have to do, you can say activity is PA over KH, right? And that's equal to gamma times molality. So if I know my molality, my gamma will just be equal to P sub A over gamma K sub H, right? Or if I say PA over KH prime is my activity, then that must be gamma times mole fraction of A. So if I know my mole fraction of A, I can solve for gamma. It's just going to be PA over, oops, this should be molality. KH times molality, and this is PA over KH prime times mole fraction. Think of it this way. This is the actual, okay, partial pressure of A in equilibrium with your solution. This thing right here, this is the PA if Henry's law is obeyed. Right? Same thing here. This KH prime XA would be the PA if Henry's law is obeyed, and this PA up here in your numerator is your actual partial pressure. So in either case, you get the same gamma because KH prime M will just be equal to KH prime K, mole fraction of M. So let's illustrate that with this problem. Let's say at 298K, the vapor pressure of pure liquid is 0.2 bar when mixed with solvent B, and you get ideal dilute solutions for mole fraction of A going from 0 to 0.1, and KH prime is 0.25 bar. So that means if we were to plot partial pressure of A over the solution from XA equals 0 to XA equals 0.1, you're going to get a straight line, and the slope of that, so if you're to extrapolate that all the way to mole fraction of 1, that extrapolates to 0.25 bar. That's your KH prime. Okay. What would be the molecular explanation for the deviation from Raoult's law? Well, in this case, your vapor pressure of pure liquid A is 0.2 bar. So 0.2 bar, right here, this is P star A, right? Oops, sorry. It's 0.2 bar. That's your P star A. So this is the Raoult's law expected curve for Raoult's law, and your Henry's law curve looks like this. Okay. So what would be the molecular explanation for the deviation from Raoult's law? Why is KH prime not equal to PA star? The explanation is that molecules of A must not like molecules of B. So they have a greater tendency to escape, so the vapor pressure of A above the solution is higher than what you would expect from Raoult's law. Okay? Now let's look at this second question. For a solution where mole fraction of A is 0.2, let's just suppose you measured it and you found it to be 0.045. Okay? What would be the activity coefficient of A in the liquid phase, assuming the vapor is ideal? So our activity coefficient is going to be P sub A over what you would expect from Henry's law, which would be, what would it be? KH prime times mole fraction of A. Okay, so what's our actual vapor pressure? It's 0.045 bar. KH prime is 0.25 bar. And mole fraction of A, according to this, is 0.2. Okay. So what is that? Let's see. Let's multiply 0.25 times 0.2 is 0.05. So that denominator is 0.05 bar. So 0.045 bar over 0.05 bar. Okay. So that means that your activity coefficient is 0.045 divided by 0.05, it's 0.9. Okay, let's relate that to what we plotted here. At XA equals 0.2, let's say 0.2 right here, Henry's law would predict that your vapor pressure is 0.05, okay? But according to this, the actual experimental vapor pressure is only 0.045, which is going to be somewhere around there. Okay, so you see the actual vapor pressure is lower than what you would predict from Henry's law. So we say the solution in this case is not an ideal dilute solution. It deviates from Henry's law. So that's the activity coefficient if you're going to use Henry's law as your standard state, KH prime. Okay, pure A with a fictitious vapor pressure of 0.25 bar as your standard state. What would be the activity coefficient if we were going to base it on Raoult's law? Then in this case, gamma, based on Raoult's law, would be P sub A over the expected vapor pressure using Raoult's law, which is going to be P star A XA. Okay? Think of it this way. Gamma times XA is activity of A. So activity of A, we said, is PA over PA star. If you're going to use Raoult's law, then that's what it's going to be, right? So if this were Raoult's law, then you'd say PA over PA star would be 0.045 bar over PA star is 0.20 bar right here. Okay. And activity of A in this case would be 0.04 0.045 divided by 0.2, which is 0.225. Okay, so that's gamma times mole fraction of A. So gamma in this case would just be activity over mole fraction of A. Okay, this is really activity right here of A. Alright, so it's going to be 0.225 over mole fraction of A is 0.2. So that is, let's see, 0.225 divided by 0.2 is going to be 1.125. Okay, so that's your activity coefficient if you were to use Raoult's law as your basis, as your standard state, pure A with a vapor pressure of P star A. Now, all right, so where is that on our graph? Let's look at what's our PA expected vapor pressure from Raoult's law. PA star XA is equal to what was it? 0.20 bar times 0.2 mole fraction, right? So this is for P star A, and that's mole fraction of 0.2. This is going to be equal to 0.40 bar. So according to Raoult's law, the expected vapor pressure here would be 0.04 bar. So you have a positive deviation from Raoult's law, but you have a negative deviation from Henry's law. The actual activity is actual vapor pressure is between what you would expect from Raoult's law and what you would expect from Henry's law. So you have a non-ideal solution as far as Raoult's law is concerned. You have a non-ideal solution as far as Henry's law is concerned.